4.4 mean value theorem for derivatives. I'll attempt to illustrate with a picture the idea behind this theorem. X. I'll draw some function f of x. All right. I'm going to pick two locations on here, A and B. Maybe A is right here, perhaps, and B is over here. Something like that. All right. So that means the point up here would be B f of B, and over here we have A comma f of A, of course. All right. We've seen pictures like this before. And now I'll draw the secant between these two. There. All right. So a small backdrop. We haven't worried about it before, but now I'd like to mention the properties this function has over this particular interval AB. And these are the conditions that have to be met for the mean value theorem to hold. 1. F of x, in my picture at least, is continuous on the interval AB, right? It goes through a continuous set of values here. There's no asymptotes, holes, or jump discontinuities, nothing like that. So f of x is continuous on the closed interval AB. 2, and that's all we need, is that my function is also differentiable on AB, right? In other words, there are derivatives, there are tangent line slopes everywhere along this curve from A to B. Now in my picture it's really everywhere, but I'm only concerned with the interval AB. So f of x also has derivatives all along the AB interval. So that would mean it is differentiable on the open interval AB. All right. If that's the case, right, if you have these two conditions met, then that means the mean value theorem will hold. So what is the mean value theorem? So it has to do with this secant. This secant we've had before. We know the secant slope is f of b minus f of a over b minus a. And this is also called the average rate of change of the function. Along the interval AB. It's not how it changes at any particular point, it's the average rate of change over the entire interval. And that's that secant slope, that's our difference quotient. So it will turn out, if we look carefully at this picture, that as we look at the derivatives, right, look at the tangent slopes, tangent slope is of course the derivative of this function. If we start looking at all the tangent slopes along here, right? There's one, there's another one. I don't want to draw them in, I just want to draw one in particular in a second. I'm going to start outlining these tangent lines and their slopes. It's fair to say that eventually you will draw a tangent line that, maybe right about here, that will be parallel to that secant line that you drew before. Maybe something like that. Okay? So maybe it's happening right about here. I'll call that C. Okay? So we see that there is a tangent line that became parallel, as you moved across here, it became parallel to this fixed secant line. If that's the case, I'll write C in here now, and then the secant slope and the tangent slope must be the same. Okay? If they're the same, then I can write then there exists a value C which was in our interval AB, such that the blue slope and the red slope were the same because the two lines are parallel. That is, the tangent slope, the derivative at this location C, is exactly the same as the average rate of change over the interval AB. That is the mean value theorem. As long as you have these two conditions met, continuity and differentiability on this interval AB, then there will be some value C, it could be more than one, but there will be at least one value C where the tangent line will take on the same slope as the secant line along the interval AB.